So yesterday we have talked about the area under the curve bound with x-axis and then two vertical lines to say like that's the area we want. Now today we talk about the area in between two curves. Okay, so you have one curve and another curve. They can have intersections and they will form an area between two curves. So in this case, I have put case 1, case 2, and case 3 here. But all I want to say is I don't care about whether the graph is above the x-axis or below the x-axis. They all calculate by the same way. Okay, you find the two intersections and you see which graph is on top. You use the top graph minus the bottom graph and integral that. So, okay, I'll just show you 3 situations. Well, first situation is like this. Okay, they intersect at A and B. Okay, that's the first one. So that's, say, top one is fx and bottom one is gx. So I mean bottom and top is for the intersection area, like this area. Okay, you can see fx is on the top and then gx is at the bottom. I know after that it's different, but I don't care about other place. I just care about for that bound area, which graph is on top. And I can see my fx is on top, my gx is at the bottom. So that's the first one. And the second one I want to sketch is okay, something similar to this, okay? So I still have fx for this one and gx for this one. And I still have intersection. Say intersects at A and intersects B. Okay, so this is the area I want. And I can go for a third one. And that's the third, yep, that's the third one. We can still have A and B. That's the fx, that's the gx. Okay, you can see from 3 of my graph, the first one, all the enclosed area is above the x-axis. The second one, all the area is below the x-axis. And the third one, part of the bound area is above the x-axis and part of it is below x-axis. But it doesn't matter. They all calculate by the same way. So all of those 3 is the area can be found by integral of A to B, fx minus gx, and then dx. Okay, they all calculate by the same way. We integral the difference between the two graphs, fx minus gx, the top one minus the bottom one, and then the upper limit and lower limit will be the intersection. Okay, will be intersection. So bottom one is the left hand side and then the upper one is the right hand side one. So if you use the top function minus the bottom function and integral between the intersections, that will give you the bound area. I don't need to see where is the x-axis. All I care about is for that area, which graph is on top, which graph is at the bottom. So that's all I need to know. Then you can see, okay, for this one is better because I have red one is the gx and the blue one is fx. And you can see I have many intersections here. I have A, B, C, D, 4 intersections. And then in between A and B, the gx is above the fx. So that's why from A to B, I should have fx, gx minus fx because gx is on top. For the section B to C, fx is on top, so integral B to C is the top one minus bottom one, fx minus gx. And then for C to D, gx is on top again, so it's integral from C to D, gx minus fx. So when there's more intersections, you need to think about which one is on top, and you need to only calculate that part and then calculate the next part. So this is by hand approach, okay? This is hand approach. Also, we can do similar things to the, like we can absolute the function, make everything reflect to the like above the x-axis, and then you integrate just from a starting point to a finishing point and always give you the total area. We can do the same thing for the area between two curves. I can just, okay, I know I start from A, I finish at D, I don't know what happens in between. I just use any function minus the other one and I absolute the value. Or I can use fx minus gx and then absolute the value. That will give me the area shade between the curve in between A and D. Okay, in between the point A to point D. So I can do either way. Okay, so if we put some absolute values, I don't need to care about all the other intersections in between. Just absolute the difference between the two functions. And then absolute that, start from A, finish at D, and just integral from A to D, and that will give you the total shading area from between two curves. Okay, so those two is by cast. Okay, it doesn't matter which one subtract which one, it will give you the same answer. Sorry. Okay, that's the just the theory, and let's have a look at this question here. Find the area enclosed by the graph of sine x and cosine x for x in between pi on 4 to 5 pi on 4. So let's sketch the sine x and cosine x graph. Just sketch in between 0 to 2 pi. You really needs to sketch to 2 pi, so that's pi. That's pi over 2, and that's 3 pi over 2. I can just sketch to 3 pi over 2. So for sine x, it start from 0. Go top, go here, go bottom. Okay, so this is my sine x. And my cosine x is go top, mean, bottom, mean here. Okay, the red one is my cosine x graph. And the area shade in between is this, which is really good because it's just in between 2 points. Okay, there's no other intersections between these two intersections, so I can just calculate it by one integral. But I need to work out what's the intersection here. I need to work out what's the intersection. So those 2 points. What I can do is sine x needs to be the same as cosine x. Then I can solve tangent x equals to 1. Tangent x equals to 1 means x equals to pi on 4. And period equals to pi. So x equals to pi. I can't have negative. Pi on 4 is my domain already. And I add another one, I will have 5 pi over 4. So this one is pi on 4. This one is 5 pi on 4. So now it's very easy to solve. We just need to integral between pi on 4 to 5 pi on 4. And sine x is on top, so it's sine x minus cosine x dx. Okay, the blue one subtract the red one, and in between the two intersections, pi on 4 and 5 pi on 4. That's what I will have. Okay, what's the integral for sine x? Negative cos x. And how about minus cos? Minus sine. Okay, good. So that's the integral. And I can sub pi on 4 and 5 pi on 4 in it. So I can sub pi on 4 in first. Is minus cosine 5 pi on 4 minus sine 5 pi on 4. Okay, so that's the first substitution, and minus the second substitution is minus cosine pi on 4 minus sine pi on 4. Okay, 5 pi on 4 is here. Okay, so reference angle is pi on 4. And that's the tangent cosine. So cosine will become minus cosine. You have a negative as well, so it's a cosine pi on 4 plus a sine pi on 4. Okay, because you need to have change it to reference angle and you need to negative the thing. So the two negative become positive. So it's your cosine pi on 4 plus sine pi on 4 and plus cosine pi on 4 and plus sine pi on 4. So they will have the same value, is 4 loss of root 2 over 2, and that's a 2 root 2. Okay, because cosine, sine pi on 4, they're all the same value, which is root 2 over 2. You have 4 of that, so it's 4 times root 2 over 2, have 2 root 2. Have 2 root 2. Okay, so if we're trying to use calculators, we can integral between, we just need to get the upper limit and lower limit correct. So it's pi on 4 and 5 pi on 4. Well, I can put any in the front, like if I don't know, like I just put absolute value here and it's definitely correct. So I can even use cosine minus sine, like if, say, I don't know which one is on top. So I just use cosine minus sine. And remember the absolute value, that will be definitely correct. So it's 2.82. So I said it's 2 root 2. 2 root 2. Okay, so they give me the same value, so that's correct. But I haven't changed my calculator into exact form. If I change it to exact form, it should give me 2 root 2. Yeah, it should give me 2 root 2. So just show you the calculator. Let's have a look at the next one. Okay, next one says sketch the graph of y equals to negative x. Y equals to negative ex, and the line y equals to 3x. And then x equals to negative 2 and x equals to negative 1. Let's sketch for that. be y equals to minus ex. And I want to sketch y equals to 3x. Okay, so I have this line is y equals to 3x. And I want x equals to -2 and x equals to -1. Okay, so that's x equals to -2 and -1. This is the area bound between that. Well, how I can know the intersection is not included? How I can, well, you know, like if the intersection is included in this region, then I need two integral to talk about it, because one, like gx is above fx and then fx is above gx. I need to use two integral to talk about that. But from my graph, like it looks like it's not including the x-intercepts. The intersections. So how I can test it is I can substitute point in. Well, similar idea like yesterday. I can sub when x equals to -2. Like this y equals to minus e -2. And this one equals to y equals to -6. So this is a more negative number, so definitely below the exponential function. And you can sub when x equals to -1. And I will have y equals to -1 over e. So that's y equals to -3. Again, this is a more negative number, so they have the same thing, like the exponential is always above the linear in between -2 to 2. So it's always like this. Okay, in between -1 to -2. So that's why I must have this graph. If this line is on this side, then the linear must be above the exponential. Okay, not like, is my exponential greater than my linear now? So my intersection won't be included. Okay, my intersection won't be included. So what all I need to do is -2 to -1 minus ex minus 3x dx. So I will have minus ex minus 3 over 2x squared to integral that. Put -2 and -1 in. When I put -1, I have that minus 3 over 2. And then minus -2 minus 3 over 2 times 4. I have 1 minus 1 over e minus 3 over 2 plus 1 over e2, 1 over e2, and then we have plus 12 over 2. And I have these two is a 9 over 2 minus 1 over e plus 1 over e squared. So I don't care about x-intercept now, I care about the intersections. Is this area include the intersections or doesn't include the intersections? So if it doesn't include the intersection, then it's easy to calculate. I can just start from the left to the right, and then one function subtract another one. Okay, next one is to use cas. Okay, write down the integral for the area bound by the graph of y equals to negative x and the line. So same question, but I want the line in between negative 3 over 2 to 3 over 2. In this case, intersection will be included. Is in the shade area. Okay, intersection is in the shade area. So therefore, I can't calculate the intersection. That's why I ask you to use cas, because I don't know how to solve this. Okay, I don't know how to solve for this. I can't find out the exact value for that one. Like, I can use calculator, but it's not exact. But if you use, you already have the calculator here, why I need to solve for that? I can directly integral that from negative 3 over 2 to 3 over 2. Absolute 3x minus negative ex, or the other way around. Okay, or the other way around. So it will be the same. So, or I can have negative 3 over 2 to 3 over 2, 3x minus ex minus 3x dx. That will be fine as well. They all give you the same answer. Just use one to subtract the other one. Use one to subtract the other one. So I can go integral negative 3 over 2 to 3 over 2. And I can use 3x plus e to the power of x and then dx. And control enter. That gives me 4.26. Okay, 2 decimals, 4.26. When we have calculators, it's really easy to calculate. I can directly do that. All right. Let's have a look at 3 first and then 2. Those 2 questions are very good questions. I think they're all real VC exam questions. Let's have a look at 3 first. Okay, 3 says part of the graph of gx looks like below. Okay, x squared minus 4 is shown below. So I have 2 areas. One area is bound between 0 until the x-intercept. So you can see my x-intercept, this must be 2. Okay, my x-intercept here must be 2. So then to a point A. Okay, to a point A, I don't know what's A. But it tells us the region A is the same as the region B. Okay, so those 2 areas are the same. Okay, those 2 areas are the same. So find the exact value of A. Find the exact value of A. So the one equation I can make is 2 to 0 x squared minus 4 dx must be the same as 2 to A x squared minus 4 dx. Okay, that's what I can have. Because it's a multiple choice question, then we can have our calculator. I can solve this directly by calculator. I'll show you both hand approach and calculator approach. So I can solve menu 3.1 to solve. Okay, solve for what? Solve for integral in between 2 to 0. So that's 0, that's 2, because it's a negative area. Then x squared minus 4 dx equals to integral 2 to A. Okay, you must use another letter other than x. Okay, so a different variable. So x squared minus 4 dx. We solve for A. Okay, we solve for A. And also you can see your restriction is your a is greater than 0. Well, you can restrict it. Well, not really necessary, but you can restrict it, like on the right hand side from the diagram. Okay, and then we have that a is 2 root 3. Okay, a is 2 root 3. So we times that in, that's a root 12. So I will have E as my answer. Okay, just 1 second, I can have the answer. So type that in, and that's a root 12. I solve out the answer. Or I can solve it by hand approach. What I'll have is a third x cubed minus 4x 2 to 0 equals to same thing 2 to a. And I can substitute, that's 0 minus, you sub 2 in, a third times 8 minus 8 equals to a third a cubed minus 4a minus that minus 8. I can expand. Expand, and you can see those two and those two can get cancelled. What I have is 0 equals to a third a cubed minus 4a times 3 a cubed minus 12a. Take a squared minus 12. Well, so you either have a equals to 0, or you have a cubed minus 12 equals to 0. So a equals to plus minus root 12. And because a is positive, so we take the positive root 12. We take the positive root 12. It's just like, I think all the numbers can be cancelled, because you can see 2 is at the bottom on this one, and 2 is also at the bottom at that one. So I think when I sub the 2, the f2 can be cancelled on both sides. So you have a minus f2 and you have a minus f2. So minus f2, they can get cancelled. And then you have f0 equals to fa. So basically I have capital F0 equals to capital FA. And then you just do the calculations. Should give you root 12. It should give you root 12. But like, I would suggest you to use calculator. If it's a multiple choice, use calculator is more convenient and it's quicker. Any questions? Anything not clear? Okay. Now I want to talk about second example. Okay, this example. This is a quite old question, but it's a very interesting one. Before we do that question, I want you to think about one thing. Okay, if I draw this graph, okay, this is a log EX. Okay, and this is 1, so 1,0. And then I will do here. Say here is 3. And the area bound by the curve and the x-axis is here. Okay, what's the integral you can give me to talk about the area I shape? Just give me an integral. Integral of 4 1 log x dx. Okay, just integral the function in between starting point, finishing point, give me this area. What's the problem after this step? If you don't have a calculator, what's the problem? Yeah, you don't know how to anti-diff the log, okay? You don't know how to anti-diff the log. So that's the problem. Yeah, that's the main problem. Like, I don't know how to evaluate. It's a correct integral, and if you put that into the calculator, okay, if you put that into the calculator, no problem with the calculator, okay? I can show you. You will have answers. Like, there will be an area bound by this curve and 1 to 4. So their area is existing there. And if you use calculator, it can find out that for you. So what we can do if we don't have calculator. So see, that's the y-axis and that's the x-axis. Okay, I'll just do this here on this page. I have a y-axis and I have x-axis. I have a log function. Okay, I'm not going to draw the asymptotes, but I can bound the area. Okay, when x equals to 4, what's the y value? When x equals to 4, what's the y value? Log e4. Okay, so I'll label log e4 here as well. And I'll shape the region I want. That's 1. And here is 0. Okay, so, well, I can't record this, but just look at this paper. Okay, this is the region I want. Okay, so shading region is the region I want. Well, like, I can't evaluate that. Like, I can't use the integral to evaluate that. So if I use the rectangle to subtract, can you see a rectangle here? Yeah? And if I use the rectangle to subtract this area, it can also give me this area, right? Okay, so what I want to do now is, well, it doesn't say like y-axis always needs to be the vertical one, and x-axis always needs to be the horizontal one. Like, not necessary to be that. If I can change x-axis to the vertical one and y-axis to be the variable, so basically x to be the subject. So x equals to something. So what I'll have is y equals to log ex. Now is y to be the vertical one. So now my x equals to ey. My x is the vertical one, right? So I will resketch the graph. Make x to be the vertical and y to be the horizontal. So if you can see this, okay, this is positive x, this is positive x, this is positive y. So my graph should look like this. Can you see that's an EX graph as well, like this side? Can you see that's an EX? And can you see this area is the white area I was talking about before to subtract. So now because it's reflected that way, and that becomes the EX graph. So I will integral the e to the power of y graph of dy, because your horizontal x-axis become y-axis. So I just integral this graph, okay, according to dy. And then the point I need is this point to this point, right? So that's the, okay, this is the white area I need. So it's from this point y is your horizontal, so the lowest point is 0 to log e4. Okay, so this point is log e4 on that side. Okay, log e4, so it's integral from 0, y equals to 0, to y equals to log e4 of dy. Okay, and I will find this wide area here. Okay, this region is this region here. So it's just go that way, and now come back. It will give you this area here. When you have this area, well, I can anti-diff log exponential. I can anti-diff exponential. I will have ey and then 0 to log e4. Okay, ey to log e4. So now what I will have is, we sub that in, that's a 0. So that's a 4 minus 1. Okay, sub that in, that's a 4. Sub 0 in, that's a 1. So that's a 3. But 3 is not the answer. Okay, 3 is not the answer. 3 is only this wide area. Because, see, you do that, the area under the curve you find is this wide area. It's not the shading region. The shading region, you still need to use the rectangle to do it. Okay, so this point is log e4. So the actual area will be found by 4 times log e4 minus the integral 0 to log e4 of e to the power of y dy. Okay, the rectangle minus the white area, that should give you the shading area. And also you should understand, the variable I can change it whatever like I like. So I can say that's 4 log e4 minus 0 log e4 ex dx. That's fine as well. That will give me the same result. Actually, I'm looking at the y-axis. Okay, actually I'm looking at the y-axis, but I can change the variable just to x. Okay, just change the variable back to x. There's no problem with that. So I can't directly evaluate the shading area here, but now I want to change the axis to make look like that. X looks vertical and y looks horizontal, and I can still find area shading here. If you really can't see it, you sketch it on a piece of paper and you can see, okay, from that shape to that shape, and you can see the area clearly bound under the curve and between the horizontal axis. Well, but in the exam we can't always see that. Okay, we can't have a separate paper and then draw it here and then see what's going on here. So all I need to do is I look things this way. Okay, normally I look at things this way, right? I look at the paper this way. Now I can look this way. Okay, you can rotate your paper 90 degrees. Okay, and then see, treat this one as the x-axis. Okay, treat this one as the vertical axis. So look at this one. So, well, let's have a look at this question here. So this is something related to this question. It's easy. I start from this example. So to find the area of the shade region for the diagram shown below, 4 different students proposed the following calculations. They are not necessary to be correct. So which one of the following is correct? So 4 proposed is here. Okay, so 4 of that. This is just an exponential y equals to e to x. Okay, this is just y equals to e to x. But, well, it's easy to see. The first one is easy. I can just use the rectangle to subtract the area below that. Okay, so I can use the rectangle, which is 1 times e2 minus the integral between 0 to 1 e to x dx, which is this one. Okay, which is this one. So this one is correct because it's used the rectangle to subtract the area under the curve, the white area, and that will give me the shading area. Okay, so this blue area is given by integral 0 to 1 to e to the power of 2x. Well, one can't be right because that only gives you the wide area. So the first one is definitely incorrect. And let's look from a different way. As I said, let's rotate your paper anti-clockwise 90 degrees. Okay, you rotate your paper anti-clockwise 90 degrees. So your x-axis become the vertical one. Okay, x-axis become the vertical one. So I need to make x to be the subject. So 2x equals to log EY. And x equals to a half. You can write that down, okay? X equals to a half of log EY. Okay, look at this way. And then now the shading region is bound with the horizontal x-axis now. Okay, it's not bound with the vertical one because you rotate it, like your y-axis becomes the horizontal one. And you can see that's just integral from 1 to e to the power of 2 of a half log EY and then dy. That's directly give you the shading region. Okay, that's directly give you the shading region. Okay, from 1 to that point and this curve, we make x to be the subject. So it's a half log EY. Again, same reason, like you flip it, make x to be the vertical, you need to make x to be the subject. So x equals to something is the equation now. And then bound between the y-axis. So this region is bound between the graph and the y-axis. So the y value is from 1 to e2. So that's why you write 1 to e2 of the function make x to be the subject. We will have this one. And you can see that's this answer. Because as I said, you can change the variable together. I can change the y to x. There's no problem with that. So I can just change this to x and then dx. Okay. After you write the integral, it doesn't matter because the y is just a variable to antidiff. So I change it to x, I change it to z, I change it to a. It doesn't matter. It will all give me the same thing. So number 4 should be correct. And therefore number 3 can't be correct because you use the same limits but you have different. Okay, so 3 is you still look at from the rotate way, but you haven't changed the equation. That can't be correct. You need to change the equation and change the limits as well. Okay, so change 2 things: change the limit and change the equation. So what we should have is 2 and 4. So D should be correct. Okay, D should be correct. There's 2 ways to look at it. Use the rectangle to subtract the wide area, or we rotate it to see y as the horizontal x-axis, and then that's the area bound with the horizontal. I can use this way as well. It's a hard thing to understand. I would suggest you, maybe if you still don't get this one, you can sketch this graph on the paper and then see from the backwards, make x to be the horizontal and the vertical and y to be the horizontal to see the shading area again on the piece of paper. Still can't get it? Tomorrow I can show you another time. Okay, any questions? Questions? Well, you need a little bit of thinking for this one. Okay, if you don't have any questions.